Okay, this is just a short segment to cover some of the material that we didn't get to say on Wednesday because of the snowstorm. So a little prelude to the lectures for Friday and Monday. And basically I just want to point out some things about using DFTs. It kind of folds into all of the theory that we end up doing with DFTs and how we end up using it. I have this wonderful computational tool for looking at things in the frequency domain, and basically what we said is if I have a discrete time Fourier transform, I have a continuous function of f. It has all, basically I got to deal with functions instead of samples to talk about this function of f that's periodic. Sampling theorem says I can always get away with sampling any function of a continuous variable provided I had finite time extent, and so I limited in time to a block of samples. I get this block algorithm that we called the DFT, right? So the discrete Fourier transform, a block algorithm. I sum over a finite length of time, but then once I've limited to a finite length of time, I can get away with collecting samples in the frequency domain. And so I end up with a frequency index k that determines what frequency I'm looking at. So there's this relationship between the discrete time frequency and the index that I get out of my DFT or FFT algorithm. So there are really two artifacts, and what I want to get down to is talking about how I've distorted things by going through this process. What's the difference between these transforms? There are two artifacts going on. One is I've limited everything in time to a finite number of samples, and the other is that I've sampled in the frequency domain, right? Okay. Now, and both of those have some implications, right? I'm going to talk a little about this limiting in the time extent because we can do some math to describe exactly how that changes our answers, right? When we talk about limiting in time, I'm only going to pay attention to the first n samples of a waveform. We say we windowed the waveform to n samples. Okay, so windowing is this idea that I'm going to take a finite time extent and only look at that period of time, window in time. So the whole idea here, the difference between dealing with a DFT and a DTFT, is that instead of using the full waveform for all values of time, I'm only going to pay attention to the values between the indexes 0 and n minus 1. And to get around to some math of that, I can say, okay, well, I'm going to define my windowed version of the function as being the original function multiplied by a window function, right? And my window function here is 0 everywhere except it's equal to 1 all the way across to n minus 1 samples. Okay, so that's kind of an easy math way to write down the signal that I'm actually dealing with when I calculate a DFT versus the signal that I'm dealing with or that I'm describing with a DTFT, which is kind of how we talked about the sampling theorem earlier. If I'm multiplying signals in the time domain, multiplying two signals together in the time domain, I can look at what goes on in the frequency domain. And so my whole concept here is that the samples that I collect in my DFT are actually sampling a DTFT not of this signal, but of this one, the windowed function, right? Okay, so here's the thing that I'm actually calculating the transform of. Here's the thing that usually I want to know about, and I'm stuck with this window function in the middle. And we can start to relate those guys. And the whole idea is, okay, if I take a transform of this, here's the function that I'm actually going to be calculating using a DFT, right? Here's my DTFT, my DFT result, right? And my DFT is not just samples of the DTFT of this thing, it's samples of this thing convolved with this transform of that window function, right? And I said the window function was a little rectangular pulse up here, right? Okay. Well, we could do some work to figure out the DTFT of this window function. And it ends up being, you know, there's a phase shift that makes it complex, right? And basically there's a phase shift here that says I've got a time delay of a signal by n minus 1 over 2 samples. There's the center of this region here, and this pulse that we're talking about is symmetric around that point. So my transform ends up having that phase shift that goes with it. That's just a time delay. And then this part over here is pretty much what you'd expect from the transform of a rectangular pulse. It's a real part of that transform. And basically it looks like a sine x over x. It can't be quite a sine x over x because it has to be periodic in the frequency domain. So I have this sine up here that's got a relatively high frequency, and the denominator isn't just f, it's sine of pi times f. So every integer, this thing actually repeats itself. Right? So the graph of this function, looks like this real curve here, and this function is then multiplied by that phase shift to delay that result. This function that I'm graphed here really gets down to what the distortion in this signal looks like. Okay, and so when I look at this transform, it has a height of n, if I take a limit there, and then these zeros are the places where the argument here becomes multiples of 1 over n. So I get 0 crossings 1 over n wide. Basically, this convolution is how my DFT gets distorted. I'm going to end up actually calculating this convolution, and what it means is this thing that I'm going to be calculating is the DTFT that I'm interested in, but it's being convolved with something like this. It tends to smear out the edges a little bit, tends to scale the amplitudes. The area underneath this thing is 1, so the average height doesn't matter much, but features that are down on the order of 1 over n, whatever your block size is, are gonna show up, right? So what we'll do is I want to talk a little about the sampling theorem. I'm going to break this right now, so I'm sure I get it within my 15-minute limit for YouTube, and we'll draw the pictures for basically going from a continuous time waveform, sampling it to the DFT, and then sampling that to get the DFT. So let me break here, and then we'll restart.